Alright, looks like we're live. About that, but you didn't expect that shit to happen yet again. It's almost every day, but it happens anyway. So, hello and welcome to another coding session. How about that? How about that? Today is what? Today is Thursday. That means today, we're doing something. Today I decided to do programming language development. So we're gonna continue developing our programming language called Bang. You can find the source code in the description as usual. So let me go open the description file. So here it is. So this is gonna be the source code. And I think today we're gonna implement a very important feature. Our language is Turing complete, but it still lacks a lot of features, right? It still lacks a lot of features. So one of the features that it lacks is an ability to work with local variables. And by the way, for those who are interested, we actually proved the Turing completeness of the language in the previous episode of language development. So you can find that previous episode on the Coding Daily channel. Hello, Poly Insecure. Hello, welcome to the stream. Hello, Apparently Potatoes. Hello, Tweetly hello. So the episode is somewhere here. Yeah, this one. So this is where we actually proved the Turing completeness of our language. Previous episode. In the previous episode. So, let's take a look at what we have in here. Hello, Sarimun. Hello, Zita. Hello. Welcome. How are you guys doing? Just let me adjust my cables and let me take a look. Do we have any changes in here or anything that I need to actually fetch? So I have a couple of stuff. So yeah, I think I was trying to make an interactive goal, but I think I actually failed at that. So yeah, I was just experimenting with what I can do in this language. All right. So let's fetch the latest stuff. I'm pretty sure there's some changes in here. It's gonna take some time. Origin master. There we go. And this one is not going to be merged right now. So if we go into the folder Bang, we have a couple of examples, and specifically we have a rule 110, which was implemented on the previous episode, and here's how it looks like. So one of the things that we lack, as I already mentioned, is local variables, right? So I already did a little bit of work by actually introducing local variables into the AST. So you can create local variables, for instance, local, right? And this thing is going to be something like this, right? And if I try to compile this example, I think it has to be something like Bang, example rule 110. Oh, I think I have to do actually something like build. Yeah, I do remember that. It will not fail compilation error. It will actually trigger an assert saying that, well, compiling this kind of stuff is not implemented, and it actually fails at a really strange place. I'm not really sure why it is failing in here, but it is failing specifically here. It's supposed to fail with oh, I know why, because I forgot to recompile my executable, but yeah. So essentially our language can parse local variables, right, syntactically. So they're part of the syntax of the language, but semantically it doesn't know how to compile them at all, right? And so this is something that we're going to implement today, hopefully, because I think being able to have local variables, even though it's not required for Turing completeness of the language, right, it is still a pretty nice quality of life feature, which was proven by decades of software development, right? If you look at any of the new any languages in the past several decades, all of them allow you to have local variables. So apparently it's quite obvious that the local variables are a very important feature in the language, even though, yet again, they are not required technically for a language to be Turing complete. Just watch the previous episode where I proved that the language is Turing complete without having local variables. You can just keep everything in global. Why not? But it's not particularly convenient, right? So even there's also a notion, something like Turing Tar-Pit, right? Turing Tar-Pit, yeah, which is a pretty interesting notion. Essentially, it's a programming language or computer interface that allows for flexibility in function, but is difficult to learn and use because it offers little or no support for common tasks, right? Essentially, you have a language that is Turing complete, but it's really difficult to do anything useful in it. So yeah, basically our language right now is Turing Tar-Pit. It's Turing complete, but it's not particularly convenient. So I'm gonna give the link to this thing in the description. Turing Tar-Pit. Hello Crimson, hello Corin Lol, a Dead Marshall, Bob the Hearthstone. Hello everyone, how are you guys doing? Welcome. Alright, so the first thing I think I want to do is maybe recompile my programming language. So I'm going to rebuild the build system. Alright, and then I'm going to just do no build, like that. Alright, so that was relatively quick, and if I try to do bang build, right, build example rule 110, yeah, it fails. Now it fails in the correct place, right? Compiling the stack variable is not implemented. That is perfect. If I remove the local variable from rule 110, I think it will compile this time, right? Because it doesn't use any local variables. Yeah. So recently, by the way, I introduced a pretty cool feature to Bang. Right, you can obviously build it into the bytecode file, but what if you just want to build it and instantly run it? What I did is essentially I implemented subcommand run, which compiles your language and instantaneously run it without saving it to a separate file. Right, so essentially it just compiles it to bytecode and instantly emulates that bytecode for you, so you can quickly just compile and run. Right, and it's statically typed still, so if you make any typos or mistakes in here, for instance, I'm gonna use a type that doesn't exist, it will still tell you that you're, doing something wrong. You can go back in here and only then execute it, and it's still not interpreted. It is still not interpreted, it still compiles first, it compiles everything, and only then it executes it. But it's just a little bit more convenient to have like a single line. You know what I'm talking about? But if you want to build it, you can just use build, and that will create you a BM file. And if you don't want to use a BM file, you can always compile it down to one of the assemblies that we have a support for. Right, so I'm gonna quickly put it like that. And there you go, you have an assembly file that you can then, you can build it, you can compile it down to ELF object file, and then link it into an actual native executable. So I'm actually thinking to make build automatically run NASM and linker for you. Right, so basically if you want to compile native executable, you will just do something like build -t native, and it will call all of these tools for you automatically. And depending on the platform, maybe it will call to different tools. Like on Windows, maybe it will look for MSVC or something like that. On Linux, it's going to look for GCC or Clang, and so on and so forth. So I want to make it as convenient as possible. If you want to compile a native executable, why not? Just compile to native executable. Hello, Kuba KL1. Welcome to the stream. So, and this is the basically assembly that got generated from this example in here, right? That's basically what it is. It is what it is, and it isn't what it isn't, precisely. So let's introduce something that is not going to work, a local variable, and let's recompile everything. And of course, I might as well actually just instantaneously run it, because why not? And as you can see, it fails in here. Compiling stack variable is not implemented. So how are we going to be compiling stack variables? I already prepared some stuff for the stack. So the memory layout, as far as I can remember, actually, looks as follows. So here's your memory. Right. Here's the memory. Here's the 0. So at the beginning, we allocate a little bit of memory, maybe like 4 kilobytes, I think, and I think it should be actually, you know, configurable for the stack, right? So here's our stack. Stack. So then we have global variables, right? So then we have a global variables. Global variables, and on a stack we actually store local variables. Local vars. It's kind of difficult for me to spell. And after the global variables, we're starting to have a dynamic variables, so basically heap, right? So something like that. Like, how do I do that? Right, this is a heap. So this is how it works. And every time you enter the scope, we're going to be actually appending local variables into the stack towards 0. The reason why we're growing the stack towards the 0 is because when the stack overflow happen, I want that to be an illegal memory access, right? I want it to be an illegal memory access so you can instantly catch the stack overflow. And here is an interesting thing. I think we'll need to introduce like a system of frames, right? So every time you enter a particular scope, we're going to be pushing some sort of like a frame on the stack. Frame is essentially going to be the place where all of the local variables start in the on this stack. So, and I think we're gonna store it like that. So before the stack even begins, we're gonna store what is the current frame. So initially it's gonna be pointing here. Then you're pushing local variables into the current scope. So here are local variables, and then you want to enter another scope by calling a function or, you know, something else. So essentially we're gonna store the address of the previous frame in here, right? Then we're gonna push all of the local variables in here, right? And then we're gonna change the address of the current frame to the current frame, right? So, and the way it's gonna be done, actually, we're gonna basically redirect this entire thing to here. So this is basically where the next frame starts. So once you're done with working with that specific frame, you go to the beginning of the frame, and you know the beginning of the frame because there's a special variable allocated in here, right? There's a special variable allocated in here. Then you go one step further, and here is where the previous frame was located, and you basically reassign it back to here. So, and then the current frame is going to point at the previous one. So we're going to use a single stack frame for each individual scope, even though it's kind of unnecessary, right? Because it's only, I think it's only needed for the scopes of the functions, right? So it's only necessary to have a frame for this thing, but it's really unnecessary to have a frame for like inner loop or something. But that will make it kind of difficult to implement, in my opinion, right? Because now, if you're not pushing the frame on each individual scope, so let me take a look at this entire thing. So it's going to be compiler, and we have a structure for the scope. Here is the bank scope. So that means some of the scopes is going to store point to like some information about the frame, and some of them won't store any information about the frame. And it's kind of like difficult. So how they distinguish when the scope introduces the frame or doesn't introduce the frame? It's way easier to think of it the way that every scope introduces the frame, at least for now. It is unnecessary, but at least for now it's going to be kind of like okay-ish. So because we want to have local variables working, right? So we just we're going to just implement enough functionality for them to work, and then we'll see how we can optimize that and make it, you know, more like better and stuff like that, how we can make it consume less memory, because push and frame on each individual scope is going to just basically consume too much stack memory, right? So it could actually consume less. So all right, so let's go ahead and implement that. So the issue that we're going to be working on is I guess compiling the variables, right? I guess compiling the variables. So it's going to be something like no build. Okay. And then I'm running it. Yeah. So this is probably going to be the issue that we're working on right now. Compiling the stack variables is not implemented. Yeah, as long as we don't try to read them or write to them, just compiling them should work. Okay, so this is actually pretty easy to implement, to separate, right? So 458. There we go. 458. So here is the scope, and I think right now, what we need to store. I guess we need to store in information of how many local variables we already pushed in there. I think yes. Yeah, I think yes. So interestingly enough, we have variables in different storage locations. So okay, that's fine. That's fine. I think it's totally fine. So let's introduce something like memory address, right? Memory address, and this is going to be like basically frame offset, or maybe frame top right is going to be basically frame top offset, right? So this is basically the information of how much bytes were already allocated on the frame, right? We don't know exact position of the frame, and this is because it may be located anywhere, right? It just depends on how you call the functions. But we do know the relative position of the variables within the frame. We only know the relative positions of this kind of stuff. So, and that's precisely what we're storing in here, right? That's precisely what we're storing. Interestingly, now when you push a new scope, right, we have a special function that pushes a new scope. Push new scope. We need to make this function to also generate some code that pushes a new frame on top of the stack as well, right? So let's see what we can do about that. So push new scope. Right, so here is the scope, we're allocating it, and then we also refer to the parent scope, and so on and so forth. And because of that, by the way, since push a new scope should generate some code, I think we need to accept the code generator in here. Right, we're accepting the code generator like this. And I suppose pop scope should also accept this kind of stuff, right? It should also accept this kind of stuff. So compile.h and it's going to be bosom. So bosom is basically the code generator, right? So bang is the context for the language, and bosom is the structure into which we're generating the final code, into which we compile and everything, right? So that's basically what it is. So void bosom, and it's going to be something like this, and yeah, let's try to recompile this entire stuff. It's going to be no build. Okay, so now every time I compile in the block, right, I'm compiling the block, I also need to provide the bosom. All right, so that makes sense. That does in fact make sense to me. There's other places where we have to do that, specifically when I'm... Oh, okay, this one is interesting. So I'm pushing the global scope, right? I'm pushing the global scope. So there is some sort of a separation between global and local scopes. So I'm not still sure how good of an idea it is, but okay, I'm gonna just provide this kind of thing. So, and let's try to recompile this entire stuff. So there's another places. So, and what is this place? Build subcommand. Oh, there's two places where I have to... Okay, that makes sense. So there's literally two places because I copy-pasted the code in both of the places. All right. Okay. Cool. So now when we are pushing the new scope, we do have the code generator, so we have to use it to our advantage. So if I remember correctly, how do I compile the stack? I think I allocate additional information not only for where this the stack frame begins, but also where the stack itself ends. And I think with the frame system, it's kind of unnecessary information. So maybe I'm gonna only store the beginning of the frame. Hello, Asset0, welcome to the stream. How are you doing? All right, so I think I need to get rid of the location of this stack because it's kind of unnecessary in my opinion. It is in fact unnecessary. The only thing we care about is where the current frame starts. And as we know where the current frame starts, knowing the offsets within the scope, we can actually calculate precise position. So all of that is completely unnecessary. Is the general concept all in your head or do you write ideas down? I do a lot of things. I keep a lot of things in my head. I write a lot of things down on a paper. I write a lot of things down in a computer. I write a lot of things down in the source code. I write a lot of things down in issue trackers. A lot of things like literally everywhere. So, and is that helpful? I don't know. So it's just like, yeah, sure. That's what I do. Thank you for the kind answer. Yes, it helps. Okay, I don't know how, but I'm really glad that it helps you somehow. So now what I want to do, I want to remove one of the variables. Yeah, there you go. So we have a stack top variable and stack frame, so basically where the frame starts. And as I was saying, I think the top of the stack is unnecessary, right? It is unnecessary because we only need to know where the frame begins, and then each individual variable knows its offset relative to the current frame, so we don't need to keep track of this kind of stuff. So yeah, so frame needs to be kept track at runtime. Top of the stack can be easily kept track at compile time, right? So, and it's like a responsibility of each individual scope to like calculate the offset relative to the frame. So I'm going to remove this entire variable and just go through the compilation errors and see what are the places I will have to update. All right, so we're preparing the variable stack. So we allocate the stack. All right, so stack start address. Is stack start address even that useful of a concept? Maybe it is, maybe it is not. I don't even know. Stack start address. Yeah, so I think I can just easily remove this entire variable, right? I'm easily removing this entire variable, and we're only allocating a variable for the frame. So we're literally just allocating this specific variable, right? So this specific variable. Cool. So, and I think that should just work now. Okay, seems to be working. Maybe we need to have like a simpler example just to see how my changes are affected in here. So we're gonna have a proc main, right? So I need to actually do something like this. And okay, I'm gonna probably just compile, right? So it's gonna be bin bang build. Okay, I really need to buy a new chair because this one is super squeaky. And this one is going to be foo bang, right? So we have a BM now, and I want to go back to debusm bin and debusm foo BM. There we go. So here is the thing. Here is the thing. So the size of the stack is actually relatively small, right? It is relatively small. And this is because I probably set it to that. Maybe I should be able to actually set the size of the stack to something like specific, especially for the development purposes. What is your language compiling to? It's compiling to its own bytecode, and we have a virtual machine that executes that bytecode. And also we have a couple of generators that can take that bytecode and generate native assembly out of it. So yeah. So I can show you how it works. So let me see. So here is the language being bang, and I can run a specific example. This example doesn't work because I'm in the middle of developing some feature, right? So there we go. So this is example called Rule 110, right? If you never heard about Rule 110, it's a cellular automaton. One-dimensional cellular automaton, which is usually used as a means of demonstrating that your language or system, a computational system, is Turing complete, because it's very simple, yet it's Turing complete. I'm going to put this entire thing in the description if you're interested. So Rule 110, and I generally would also recommend you to watch my previous episode on this language development, where we actually were implementing this entire thing. So this is Rule 110, and it just generates this pretty picture, right? It just generates this pretty picture. And as you can see, it's the result of the execution of our language. What I can do now, I can try to compile it to our own bytecode, and here is the file with the bytecode. I can execute it with our virtual machine, or I can generate assembly out of that bytecode. So these are all of the assemblies and platforms that we support right now. So you can grab one of them and just basically generate assembly out of this language, right? There we go. So here is assembly. Then it's actually NASM, right? So you have to compile it with NASM 64, Rule 110 ASM. So this is going to be, here's the object file, and then you can link that object file into the final executable, like this. Here you go. You have a final executable, which is a native ELF 64-bit executable, statically linked and not stripped. It is statically linked. It doesn't even depend on libc. It's, yeah. And if you try to execute this entire thing, it's going to produce the same pattern as it was producing when it was emulated. So that's how it works. Language is obviously not finished, so in the future it's going to be way more convenient. Thank you, FDICUK, for raiding me with 8 browser tabs open. Thank you so much. I really appreciate you opening so many tabs. All right. Does it answer your question, by the way? So in terms of like what this language compiles to, it compiles to our own bytecode, but then we have a couple of generators that can take this bytecode and compile to specific native platforms. And the cool thing about this bytecode is that it's cross-platform, right? If you manage to compile your emulator on a specific platform, you can then execute it on that platform. It's like JVM. You know what I'm talking about? It's like JVM, but then you can generate native code from that JVM. Hello, Braga Matt. Welcome to the stream. All right. So let's continue. Bang compiler. All right. So everything seems to be working. One of the things I wanted to do for this language is actually maybe customize the stack size, right? because right now the stack size is hard-coded, right? It's 32 bits, bytes. The reason why I put 32 bytes in here is because I want you to test things, right? So basically I want you to generate some code, and I don't want to scroll through a huge stack. But to be fair, in production I want to have like a big stack, like around maybe 4 kilobytes or so. But it's very inconvenient for the purpose of debugging and stuff like that. So maybe the first thing I'm gonna do, I'm gonna make the stack customizable through a special flag in the compiler, if you know what I'm talking about. So let's introduce some sort of a special flag. All right, so let me go to the compiler itself. I think it's somewhere in here, and we're gonna introduce that stuff for the build subcommand only, not for the run subcommand. I think run subcommand is going to use the default stack, right? So usage, build usage. Okay, so here are all of the flags in here. Provide output path, then the target, and so on and so forth. So, and let's print the following thing. So maybe it's going to be S, and in here we're going to provide bytes. Stack size, local variables stack size in bytes. Okay, so this is basically what we expect in here. Build usage, right? Build usage, and all right. So else if strcmp flag s, if it's equal to s, we need to actually set the current stack size. So we have input file path and output file path. Now we need to introduce the local, maybe stack size. Okay, so this is going to be stack size, and by default it's going to be 496. Maybe I'm thinking it would make sense to have a macro for the default stack size. Right? Define default bang default stack size, and it's going to be 406. And the reason why I want to have a macro for that is because I want to print that macro in the help. So something like default zu bang default stack size. There we go. So I want to be able to do this kind of stuff. Stack size, there we go, and this one is going to be default stack size. It has to be bang default stack size, there we go. And if the user provided -s, we have to check if we still have any arguments, right? So we need to print build usage std error, fprintf std error. No value is provided for flag s, and it's going to be something like this, and then we're going to exit with 1. Alright, so after that I'm going to change the stack size to the one that is provided by the user, but that means I need to convert the string to an integer, right? So const char stack size sister, right? So I'm gonna do shift argc argv. So do we have some convenient functions to convert string to unsigned integer? str to u, there is actually. Is there something str to size? Maybe not. Okay, so str to u, convert the string to uint max t, and it's actually library bsd or something. It's not part of the standard, I think. I think it's not part of the standard. Maybe it is. Maybe it is not. There is a lot of a to I, a to l, a to d, but I want the one specifically that can convert to size t, if you know what I'm talking about. So c string to size t. So all of them convert to integer or something very specific. Size t is sort of like fluctuating. Series. Well, I mean, I could probably use scanf. You can use str to umax to perform the conversion. Maybe. Is that part of the standard? I think it is. Gio, what's up? Hi. How you doing? Welcome. Hello. I'm just trying to convert the string to size t. I have a massive headache from using the Shady IDE. Yeah, so it's the Vivado thingy you guys were talking about on Discord. Yeah, I can imagine that. Is it something like Eclipse based or something? I don't know. Is it based on anything? Oh shit. Oh, it's not. Okay, so that means it's a little bit better. So a lot of IDEs, like, they're also Eclipse based, and as a person who actually commercially wrote plugins for Eclipse, this shit fucking sucks, like, holy fuck. IntelliJ. Alright, so alright, so we're just implementing local variables. It might use the Eclipse editing component, but I can set it to use an external editor, so it's fine. Oh, alright, that's good, good at least. Yeah, so this kind of IDEs, I know what you're talking about. They suck a lot. Alright, so I'm trying to use this function to umax. Fixed with integer types, C99. Maximum with unsigned integer type. Okay, so maybe this is what you want to have, just maximum type, and then convert it to size t. So that probably makes sense. Restrict, by the way. Haven't seen that one in a while. Alright, so I think I'm gonna just provide stack size str, and then we can provide the pointer to the end. Right, so it's gonna be end ptr. So end ptr, and base is obviously gonna be 10, right? And we can assign that to the actual stack size. And if for whatever reason, so I do remember the function just like on success the convert value said if nothing was found to convert, 0 is returned. On overflow or underflow, int max is returned. So I do remember there's something about end ptr, and they don't even mention end ptr. So it's like str to l. Okay, so maybe this is where it is explained. If str stores the address of the first invalid character, if there is no digit at all, stores the original value of pointer. If end but end is null on return, the entire string is valid. Alright, that's actually pretty cool. So because we expect the entire string to be valid, so that means if end ptr, while being dereferenced, not equal to 0, right? So that means the entire string is invalid. Unless you provided something like empty, right? Unless you provided something empty, but we can actually experiment with that. This one is very interesting. Okay, so let's see if we can what we can do in here. So it's going to be stdio. So here is the example, and then we're going to have stdlib int main. So it's gonna be something like that, and then I'm gonna return 0. So const char sister, and it's gonna be 69, right? And then we just provide the sister and just a character to end pointer, right? Initially it's gonna be null, right? Then I want to have size t result. Why did I put 0 in here? I didn't mean to put 0 in here. Okay, so, and I want to print a couple of things, right? First, I want to print maybe the position of the pointer. So I'm going to print 2 pointers, sister and end pointer, right? Then I want to print the dereferenced thing in end pointer, right? The dereferenced thing, okay. And then we can print the final result, right? So this is going to be something like ZU, the final result. There we go. So if I compile this entire stuff, what kind of errors are we going to receive? Okay, so I think I need to include something like int types, right? So int types.h, right? And let's execute this entire stuff, right? There we go. And everything works correctly. So these 2 pointers are not equal to each other, right? That means we consumed everything. The end pointer points at 0 and the final value is 69. So if I provide something like ABC, right, both of the pointers are equal to each other, right? They are equal to each other. The end pointer actually contains 97, which is probably ASCII code of A, so it points at the first invalid character, and the final result is 0. So you can use the end pointer as an indication that whether you completely parse the string or not, unless your string is absolutely empty. In that case, both of the pointers are going to be equal to each other, and the end pointer is going to point at 0, right? If I understand correctly. Yeah, there you go. So even though it points at 0, you still didn't parse anything, right? It's still not a valid character. So I think the actual condition for checking that you parsed everything correctly is going to be if str not equal to end ptr and end ptr is equal to /0, right? So /0 basically indicates that you reach the end of the string, right? But if your string is empty, it is trivial to reach the end of the empty string. So you also need to check if the position of the beginning of the string is not equal to the end where you stopped parsing. Okay, so that's going to be the actual condition in here. All right, that makes sense. And if this condition is false, that means, you know, we did a fucky-wucky and probably oopsie-doopsie. All right, so let's see what we can have in here. All right, so if stack size sister not equal to end pointer, actually maybe equal to end pointer or end pointer not equal to 0, right? That means we did a fucky-wucky and oopsie-doopsie. So we're gonna do something like build usage, std error, and then we're gonna print something like std error. And we're gonna print this is not a valid size of the stack, right? And we're gonna precisely print this thing, and then we're gonna exit with 1. So there we go. All right, so now we have a special flag which you can use for customizing the stack, right? We can use it for customizing the stack. Let's try to recompile the entire compiler and see what's gonna happen. So it's gonna be no build and yesu kavoye desu. This one is ZU expected but 3, so it thinks that this thing is an integer, really? All right, I can just cast it to size t then, if you want. Sure. Oh, wait a second. Is there like okay, whatever. I see what it's trying to say. Variable is not used. Okay, perfect. Perfect. So, and now I need to actually use the stack size when I'm generating everything. So I suppose I'm going to be accepting the stack size when I'm generating the variables. Yeah, here. So we're gonna accept stack size in here. So we also have a scope wars capacity. Star Over subscribed at tier 1. Thank you so much for 3 months of tier 1 subscription. Thank you, really appreciate it. Alright, so we had a stack size or something. Yay! Okay, bang stack capacity. Where is it defined? I don't remember where it's defined. I think it's defined somewhere here. And yeah, we're gonna actually remove this from here. Right, you have to specify the stack yourself. Okay, so this is gonna be a stack size, and essentially we're gonna be just using this stack size like that. Stack size. So, and this is precisely what we're using in here. So run command, in run command there is no way to customize the stack, but maybe there should be a way to customize the stack. So I'm gonna just use the bang default stack size, and then I'm gonna put it to do. There is no way to customize the stack size for bang run command. For bang run command. There we go. Hello Star Over. Thank you so much. How are you doing? All right. So prepare a stack, and here I can just specify stack size, right? Because the stack size is defined before. All right. So that makes sense. All right. So now we have a customizable stack size, which is pretty poggers, is it not? I think it is. So now I'm gonna just do bin bang, and if I take a look at the help, there we go, you can provide the stack size in bytes. So what I'm gonna try to build, I'm gonna try to build a stack with a single byte, right? So the size of the stack is gonna be single byte. And what I'm gonna try to build, I'm gonna try to build full, right? So I managed to build it. But unfortunately, I cannot see shit in this mist, so that means we'll have to go and disassemble it. Right, so debasm bin debasm full bm. There we go. So we can clearly see. So this is how many bytes we have for the stack frame, but the size of an actual stack is actually 1 byte in here. So we can try to increase the size of the stack by 2, and now as you can see it's a little bit bigger. So now I can say, okay, I want a stack of the size 32. Okay, so it becomes bigger. What about the stack size 64? Nice. If I try to actually remove the flag from here, that will kill my Emacs, because the default stack is going to be 496, and Emacs is incapable of actually displaying so many characters reliably in this particular window. I can even demonstrate you. So I'm removing this entire thing, and my Emacs is frozen. So yeah, very good editor. So if you want to be as an epic of programmer as myself, you must learn this shitty editor. Oh, so it actually managed. You guys think I'm using Emacs because I think it's a good editor. It's actually a pretty shitty editor. So I made a lifetime mistake of actually investing time into learning this piece of software, and now I'm actually have to pay for my mistakes. Right, so if you're learning Emacs because you think it's cool because I use it, please stop. I made a mistake, don't repeat my mistakes, okay? So the only reason why I'm still using Emacs, I just want to show you what's gonna happen if you invest time into learning this piece of shit. So that's basically what you will have to deal with every fucking day. just stop and use Visual Studio Code. I try to use Visual Studio Code. The main problem with it is that it has a really low responsiveness. I type very fast, and if there is a little bit of the delay between like keystrokes and appearance of the character on the screen, I cannot use that editor. And unfortunately, Visual Studio Code, being a browser, does have a little bit of a delay, unfortunately. So. All right. So let's see. This is gonna be S12, and yeah, finally I can customize this kind of stuff. All right, so let's do a committee. So I actually want to separate the scope related stuff from the stack size related stuff. So let's quickly do that. All right. To be fair, I might as well actually commit everything, yeah, because I didn't really introduce anything super significant in terms of the scope compilation, so it should be fine, I guess. I guess it should be fine. 458, introduce customizable stack size for the bang build command. Right. Shit. One character doesn't fit. You know what that means? That means that character is going to be actually cut out by GitHub and moved to the description. So I guess we can violate the grammar of English and just remove the, because it doesn't convey any information anyway, so whatever. Introduce customizable stack size for bang build command. Okay, so that makes sense. Who needs articles anyway? Like, look. In Russian language, we don't even have any articles. Like, at all. Like, it just doesn't exist. Because we Russians realize that they don't convey any information, we just get rid of them. Easy. So... Hi, are you on a ketogenic diet? No. Also, what do you think of the Dvorak layout? I have no opinion on Dvorak layout because I never tried it. So... Hold my German. Caveman speech, yeah, thank you very much. Cheers, by the way. Russian language also got rid of the to be verb. You know how in English there's a to be verb? Essentially between the subject and verb, you have to... Actually, between the subject and object, you have to put to be verb. Like, my name is Alexei, right? So it's easy to be. In Russian language, you also got rid of that. So we don't have articles, we don't have the to be verb, and you just say whatever you want to say, okay? Without any like additional stuff, right? Without any bureaucracy, just say what you wanted to say. You don't know Russian. Okay. Well, I mean, there is a verb to be. We just don't use it as often as any other languages. It's, to be fair, as far as I know, the verb to be in Russian is the same as in Polish, which is jest. But again, we don't use it as often as Polish people use it. Alright, so what do we have in here? What I want you to do now, I have the variable that denotes the frame. And when I push the new stack, Okay, so let's put it like this. So stack. Frame pointer currently points at here. Right, so essentially what I wanna do, so there's two cases when the when the scope is global and when the scope is not global. So maybe I'm gonna imagine that we have a non-global scope just to make it a little bit easier, right? So we already have something in here. Right, so that means the top is somewhere here and you already have some things in here. Right. So essentially you are located in here and your stack frame actually points to somewhere here. So this is where the frame starts. This is where the frame starts. Now, to push a new stack, you need to figure out this address. Right. You need to somehow figure out this address. To figure out this address, you need to read. So this is the frame. Frame. So you need to read frame. So read frame. Then add this offset. Add the offset. Right, add the offset. Add the offset, and there you go, you figured out this specific address. And that's gonna be the address of the frame after you actually factored out how you're gonna store this entire stuff. Right, because after that, you need to push the pointer to the previous address in here, right? So you have to do it like that. Right, that means the actual address is going to be located in here, right? So that means you need to add, let's put it like this, push, push I said, current frame, right? Push current frame, so that's another thing, like this. And then here's your new frame, it starts like somewhere here. And you need to now redirect the frame to here, right? So essentially you'd have to do something like this. You're redirecting this entire thing like that. So, redirect. The frame. Right. Redirect the frame. So that's basically 4 steps that you need to do in here. Right, so read the frame, but it's only for like a push scope, right? So that it's a push scope. So it's when you're trying to push the scope. When we're gonna try to pop the scope, we're gonna have different sequence of actions. Pop the scope. Right, so we're gonna do pop the scope. So the first thing we need to do, we need to figure out where the frame starts. Right, it's the same step in here, so we need to read the frame. Read frame, but unfortunately the frame actually points at here, but we need this thing. So we need to actually step back. Right, we need to step back to read the previous position frame. To read previous frame. Right, so this is going to be the previous frame. So we're reading this thing, and what are we doing with this thing? We essentially setting it as the current one, right? All right, so that makes sense, I suppose. It's actually easier. Right. set prev as current. So that's essentially what we need to do in here. All right, and that only for non-global scopes. That's only for non-global scopes. Interestingly, when you start a global scope, right? When you start a global scope, you can probably do that. Oh yeah, should be fine. Oh boy. All right, so it's a bit complicated, but I think we should be able to implement that. All right, so it's somewhere in the push scope, right? So push scope. Maybe it's also somewhere in the compiler. Push this scope. Push new scope. All right. Arena bank scope. Here's the new scope and what not. Read the frame. Okay, so the frame is located at where is my thingy? Bang. Stack frame variable address. This is where it's located. So that means here is the first step, and we're essentially just doing BASM push instruction, right? Instruction BASM, and the instruction is going to be read 64 bits, I think. It's going to be 64U, and it's not going to have any specific operand, right? So it's going to be something like this. All right, so, and as far as I know, read actually accepts the address of the variable it's trying to read from the operand stack, right? So that means we need to push something like push instruction BASM instruction push, and what we're pushing in here is actually word U64 bang stack frame variable address. There we go. So it's kind of interesting how I'm just programming in BASM but through C. That's what essentially doing. I'm programming in BASM but through C. It's kind of interesting. All right, so after you perform the read, on the top of the stack, we're going to have the value, right? The actual value in here. And what do we do with the value? It is a little bit dang. Yeah, programming in C with BASM, it is kind of dang. Inline BASM. By the way, I was actually thinking that maybe Bang is going to support inline BASM, and because of that, I will be able to get rid of the BASM completely, right? So maybe the BASM itself is going to be completely obsolete because Bang supports BASM inline, right? So it's kind of interesting. Imagine Java, but Java also supports inline assembly of its bytecode. So that's kind of an interesting idea. Not a platform-specific assembly, but the assembly of the intermediate representation. I've never actually seen any language do that. You know what I'm talking about? It's kind of an interesting idea. So, right. But the problem is that intermediate representation can change, and that means intermediate representation becomes like your API, and it's like restricts you a lot, so. Okay, sure. This shed, by the way, does look like a pretty cool thumbnail, I think. Maybe we're gonna use that. The face for the thumbnail, I don't know. Alright, so the second thing, add the offset. And the question is, where can we even get the offset? Surprisingly, there is no way to inline LLVM-IR in Clang. Yeah, again, I think the reason why you can't do that is because it's kind of like limiting your development, because now you cannot easily change your intermediate. Well, wait a second. your Clang intermediate representation is already used by so many people, so it is part of the Clang interface, and it is already difficult to change because you need to be aware of all of the users of that intermediate representation, right? So because of that, why not just allow to use it in the language? I mean, I don't know. But I mean, it's not a standard feature, right? So in C, it's going to be definitely not a standard feature. But some other language that depends on LLVM may allow using like inline representation. Yeah, it's not really a moving target. Yeah. I don't know. So for C, it doesn't make any sense because maybe it's like going to be completely non-standard and there's no benefit in that. I don't know. But we're going to allow that. We're not LLVM. We're not LLVM. At the offset. And here is an interesting part. Where can we get the offset? The offset is probably located within the current scope, right? So let's take a look at the bang. Increase lentils chat. Bang scope. Why do I hear human noises? Disgusting human noises. Okay. Bank scope. Where's my bank scope? There it is. So frame top offset. So it's offset from the current frame, which does make sense. So that means I need to push this entire thing. Bosom push instruction, bosom instruction push. I'm pushing the push instruction. Think about it. Pushing the push instruction. Okay, so, and what I'm specifically pushing in here, I'm actually, so this is the parent. So I'm setting the parent for that, and so on and so forth. Okay, so here's the trick. I need to do scope meta, yeah. Look, this is even bigger meta. I'm pushing the push instruction to push a local variable on the stack. You see what I'm talking about? So it's a like double meta. So scope, frame top offset, frame top offset. There we go. And here's an interesting thing. If scope is equal to null, which it can be, right? It can be equal to null. That means we are in a global scope. How to, like, okay. Pushing frame for global scope is not implemented yet, right? So essentially, if at that point the scope is null, yeah, we don't have like a frame top offset at all, so we don't really know what to do in this particular case. But maybe if the scope is null, we can just use like 0 for specifically for that. All right, so we push that entire thing, and the next thing we need to do, we need to add it to the address of the frame, right? So specifically, we're working on the second step, add the offset, right? So add the offset. All right, so it's gonna be something like push instruction, bosom instruction plus u. But we don't have plus u, but we do have plus I, because in 2's complement it doesn't matter. Alright, so, and this one doesn't have any operand, because the operands for the plus are on the operand stack. Okay, so I just calculated the beginning of this thing. I just calculated the beginning of this thing. Oh boy, alright, so that means now I need to... I need to add a little bit more information to accommodate the frame. Right, alright, so let me see. So I need to visualize the process yet again, because this is a little bit messy. So I want to do something like this. So we have something like that. So this is where we have all of that. So the actual frame is located somewhere there. So here is the actual frame, and then here is the actual offset. All right. So this is basically the case we're working with. So this is the frame. And it points at specifically here. So what we did, we extracted the address of this thing. We then calculated this address in here. All right, and now we need to push the current frame. So basically we need to now do something like this. So essentially we need to add not add. I already screwed up. We have to do minus I because we're growing. Yeah, I almost made the rookie mistake of growing this stack to the positive, and yeah, I almost fall into the trap of endless debugging of the shit. Classic, am I right? All right. So 3. Read frame address. Offset the frame address to find the top of the stack. Right, we found the top of the stack, and then allocate memory for to store the previous frame address. So that means I need to push bosom instruction push 8 bytes, because the pointer is actually 8 bytes in here. Do we store the sizes of this kind of stuff? Can I just take a definition of the pointer or something like that? Yeah. To be fair, I don't know. I'm gonna just put 8 in here, and maybe I'm gonna put it to do to get rid of the magic number of the size of the pointer. Okay, get the actual size of the pointer from the definition of the PTR type, right? From the definition of PTR type, because here we have like a huge table of the type definitions, but yeah, there we go. So we can get the size from there. All right. So I push that, and then I want to push instruction bosom, instruction minus I, right? It's going to be word use64 0, because it's not going to have any parent. How did you lose so much weight so quickly? You're like supermodel. Really? I don't know. I just stopped eating carbs for several months, so that was actually pretty easy. And we've got a raid from Kunas Stefana with 94 browser tabs. Thank you so much for raiding me with so many browser tabs open. I hope your computer is okay. Hello everyone. We're developing our own programming language. You can find the link to the source code in here. So, and we're in the middle of adding support for local variables. So yeah. Cheers, by the way. Alrighty. It's what ketogenic diet is. Ketogenic diet, as far as I know, does not... Is it? I also stopped eating fats, so... But I mean, right now I'm actually eating everything. Carbs, fats, and proteins. So... I just ate nothing but proteins for like a couple of months just to lose as much weight as I can, and then I switched back to a normal diet. So it was hard, by the way. It was hard, but because the problem with always eating only protein is that because the body doesn't have any source of energy, so it starts to consume itself because it tries to find some energy to survive. So that's essentially what's happening. Alright. So get the actual size and so we allocated some, yeah, all right, so we updated the pointer, right, and the thing we want to actually do now, all right, we want to take the current value in here, we want to take the current value and save it in here so it points like this. We're usually eating far too much carbs nowadays. Yeah, it's true, actually. When I stopped eating carbs, and after some time I just ate like a bowl of rice, I realized how much energy is contained in a simple bowl of rice. It's insane. Because we consume carbs so much every day, you don't even feel how much energy like every meal has. I don't know if I can express myself properly, but yeah. Pog, your energy says right reactors. Yeah. Pasta. That sweet, sweet umami. Oh. All right. So, what does this mean is that we have a address on the stack. I don't remember how my write instruction works, by the way, so I'll have to probably look it up. bm soc bm.c, so write, so specifically I probably need write 64. So the first thing is an address. This is actually kind of perfect because that's precisely what we have in here. I think the stack looks like this. Alright, so we have the frame address, right, so here's the frame address. Then we do an offset, alright, and then we subtract an offset. Okay, cool. Then I push 8 and I subtract 8, so I have an address in here. Which means now I want to actually store some value in there. Right, so I think I want to clone this entire thing. So we're going to do bosom push instruction bosom instruction dupe. Right, so that effectively duplicates what we have on top of the stack. 64. So, but now I need to save whatever is located in here. So that means I need to read it the second time. I really need to read it the second time. Hello, RDB42. Hello, hello. So that means I need to push the frame address one more time. Frame address one more time. Then then I suppose read it. Actually, yeah, so this is the frame. And then if I do the read, it converts it into the frame address, and now I can do the write. Push instruction, bosom, instruction, write 64U. Well, you don't have to do U, it doesn't really matter for writing. It means for reading, because you need to maintain the trail of ones in a negative values if you're using 2's complement. Right, so it's gonna be word U64, like this. And that effectively consumes these 2 top frames, right? Something like that. All right, so we saved everything. And I suppose now we actually need to save that value back to the frame. We need to save it back to the frame. And this is already the fourth step, I suppose. The 4th step, so it's gonna be something like this. Redirect the current frame. Man, that's really hard. Like, I didn't realize how hard this kind of stuff is. Just to store local variables and shit. It's all needed just to be able to, you know, to compile them. I wonder if, like, how much, what's going to be the size of the program after you're done, like, doing this entire stuff. It's probably going to be insane. But maybe we're going to optimize that a little bit later. Alright, so let me continue. This one is going to be something like that. So that means I need to get the frame yet again. Right, so that means I need to do something like bosom push instruction, bosom inst push, word u64, bang stack frame variable address. Right, so this is going to be frame. And I think we'll have to swap these 2 things, right? Because first should come the address into which we're writing, and then the value that we're trying to write. All right, so it's going to be bosom push instruction, bosom inst swap, and we're swapping u64-1. There we go. So after this, we just swap them around, right? We just swap them around, and bosom push instruction, bosom instruction write 64 without any operand. There we go. So something like this, and that consumes both of these things. All right, so that's what it takes to push a new scope, right? That's how much stuff you need in here. And I wonder if we can write this kind of thing maybe in Bang somehow, and compile it down to bosom in here. I don't know if it's a good idea to write it directly in bosom like that. So, and now we need to do the pop. I'm actually thinking, so what if the scope is null? Can we just set the offset to 0? That's really the question, because that is kind of needed for the global scope, right? So I just want to go through the entire process and see if it's gonna work for that. So, so initially, stack looks like this, right? So it starts here, right? And then we have the current frame, which points to itself, right? So the first thing we do, we read the frame, we offset the frame, right? And we offset it to 0. And then we also push the current frame, which actually creates like this kind of thing that points back to here, right? And then we reset this thing to here. All right, I think it seems to be working. And as you sort of push this thing. Okay, so I think if the scope is available, you use frame top offset, otherwise you can use 0, right? So that's basically it, and I think that should work. But we need to test how it is, well, if it performs even correctly, because I have no idea if it performs correctly. And the question is, how can we even test that? That's a lot of overhead just to call a single function. It's a lot of overhead. So it's kind of interesting. It reminds me about the old times when people were writing in C and were trying to avoid function calls, because the function call introduced a lot of overhead for the old computers of the time. And maybe that's precisely the reason, right? Because there was a lot of actions and access to the memory. And since computers were slow, this kind of stuff was slow as well, right? In modern computers, like, everything is cached in the CPU, and accessing this kind of stuff is just not like a no-brainer at all. But for the old computers, like, doing all of that stuff, constantly reading, writing to the memory, and yeah. Function calls give overhead, gave. Well, they still give, but it's negligible, so don't worry about it. Don't even think about it. I'm talking about 1970s, 1960s and stuff like that. So just like 50 years ago. Don't worry about it. Computers were completely different, and they work completely differently. So yeah, don't worry about it. These days you can even program in JavaScript and be fast. So yeah, don't worry about the overheads. Hertz and Plus, what's up? How are you doing? Cheers, by the way. It's just like I'm trying to look at the times through look at the code through the lenses of that time, trying to understand why people were doing the things we're doing. Branch ticket prediction changed. There's no branching in here. I don't know what you're talking about. Where does one learn how to do low-level things like this? On the internet. Seriously, on the internet. And believe it or not, you are doing it right now. You are in the process of learning the low-level things, because you stumbled upon the content that sort of like involves this kind of stuff, and the more you stumble upon this kind of content, the more you Google things, the more you pick up the things, the more you learn. So you're doing it already. You don't need to ask a question how you do that. You're doing it right now. Because if you didn't stumble upon this stream, like, you wouldn't be learning it. But now you're learning it. So that's how I learned it. I was just like wandering around the internet, stumbling upon things, and that's how I learned all of that. And that's what you're doing right now. And I also didn't understand the thing. Just give it a time. If you stumbled upon something and you don't understand it, don't stress about it. Just walk away for maybe a month, year, 5 years, 10 years, and eventually maybe you will stumble upon this thing again, but with a different set of knowledge, and you will understand it. If you don't understand something right now, maybe the time has not come yet. So don't stress about it too much. You don't understand something, just give it some time, right? But be careful, like, difficult thing may take more time than expected, right? So, I don't know, like, I have 15 years of software development, and I only understood how to do this kind of stuff after 15 years. So, you see what I'm talking about? So you have to be prepared. You have to be prepared. To wait a lot of time, because that's exactly what I did. It is what it is, and it isn't what it isn't. I've seen a rule for programming that line of code should have to make 80 characters. Why don't respect it? The question is, why respect it? I say that the line of code has to be no bigger than 169 characters. And everyone has to respect it, because I said so. You see how stupid it sounds? Somebody somewhere said a thing. I also can say things. I have a mouth. well, not to disrespect people who cannot say things, but if you can communicate ideas, you can effectively say things. Just because somebody said something on the internet, why do you have to listen to that? You see what I'm talking about? See what I'm talking about? All right. If you don't split your editor screen in two, you don't need to bother, I guess. Yeah, to be fair, like this kind of rule, it was invented like when the monitors were different, computers were different, everything was different. So we live in the modern days. Alrighty, so I want to test this thing and see how it goes. So we need a simple example, as already mentioned. So the size of that simple example is going to be maybe 64, and there we go. And it didn't even produce anything because it didn't recompile my code, of course. So let's recompile it. So scope, it has to be bank scope. That makes me feel happy because my line of code are longer yours. I'm trying to develop good habits. Okay, try to think about it this way. So from what I heard, I can see that you just heard some rule on the internet and you accepted it as a good rule and now you try to follow it. This is a wrong mindset in my opinion. So if you hear somebody saying, okay, this is the good practice, before accepting it as a good practice, try to understand why it is a good practice. Why 8 characters? Can you find any specific reason in 2021 to say that it's a good thing to have lines like that? Is there any arguments for that? Like, what? So, you see what I'm talking about? Take everything you hear on the internet with a grain of salt, right? So, the thing about the internet, anyone has an access to the internet. Anyone, and anyone can say anything on the internet. You're hearing something on the internet and you're accepting it as a good practice. Anyone can write on the internet. People say bullshit on the internet every freaking day. Come on! You need to filter things. You need to think. Think! You know what I'm talking about. Alright. But my boss says 8 characters limit. Okay, boss is a completely different situation. Boss pays you for your work. Right, you're providing your boss your services and boss pays you. Part of your services that you provide to your boss is following the guidelines. It doesn't matter the reasoning behind the guidelines. Guidelines exist and you're paid to follow them. This is a completely different situation. So, you're getting paid for following these guidelines and there's no reason to question them, to be fair, right? But if you're developing your projects, see what I'm talking about? You guys are getting paid. It's a good question. Alright, so redirect the current frame. Okay, did I compile my shit? I think I did. Alright. So the next thing I want to do is... yeah, there we go. This is how much overhead we have for a single call. I think. Yeah. Nice. So how many instructions do I have in here actually? So maybe I'm gonna do something like bosom mode. 26 instructions, right? 26 instructions. And do I really have 26 instructions in here? Doesn't look like a correct thing, in my opinion. Right, so if you just compare, maybe it is 26, who knows? It's 13, so where all of that stuff coming from? It's a little bit sus, don't you think, chat? It is in fact a little bit sus. So if I remove this entire stuff, right? So if I remove this entire bullshit, def sussy, yes, sussy, very sussy. I need to recompile the entire compiler, of course. Okay, it doesn't have any bullshit in here. Yeah, so it seems like it's pushing more shit than I would expect. Right, why is it doing that? Oh! Yeah, I know. Because we have two scopes in there. Yeah, we have two scopes in there. So there's a global scope, right? And it pushes this thing for the global scope, obviously. We have... Yeah, 26, 13 multiplied by 2, 26, right? So yeah, it pushes the global scope, and then it pushes the... okay, that makes sense. That makes perfect sense already. So what I'm thinking is that if it's a global scope, don't try to push a frame anywhere, right? So this is going to be a global scope. So that explains everything. At least I now understand what is going on. So if the scope is available, relative to which you can actually set everything up, only then push the frame. Otherwise, don't. Otherwise, don't. Alright, so let's put it like this. And now that makes sense. So this is how many instructions you need to push a single frame. Alright, so we're simply pushing a single frame. So, and if I take a look at this thing, you have 13 lines in here, 13 instructions, and these are the instructions that we're pushing, 13 instructions. Perfect. So we're reading the frame, pushing like 0 or something, I suppose. Why are we pushing there? Wait a second. I think I'm a dummy. So yeah, we're only pushing the... Yeah, the offset is actually... For that one is going to be 0. Yeah. So we're never going to be modifying that specific offset. Okay, that kind of makes sense. I wish we had like a debugger, very convenient debugger, where we could visualize the entire process for each individual step. But I'm not sure. So maybe. Let me see. BDB. Maybe BDB will help us to visualize this entire stuff. I remember it had a memory stuff. Yeah, I remember it had a memory stuff. So let's quickly do that. So tmux bm and we're gonna go to the bang. Maybe I need to actually rebuild the entire thing, the entire project, just in case. Not just rebuild anything. Alrighty. Bang. BDB being BDB. And I'm just providing full BM. So BDB does not... This is actually nice. I really like that. It even tells you like the issue where. Okay, so break set breakpoint as a label, and can I break on? Do we have main? Oh, we don't even have a main, unfortunately. Right. So, but I mean, it's not that big of a deal, I think. 0, 1. Because what I can do in here, right, is just copy paste this thing in here. 0, 1. 13, and I think it's gonna be 14. So yeah, I can break at 14. So yeah, this is how we're gonna be doing 14. So this is the entry point. Cool. So what else do we have in here? Inspect the memory. Inspect the memory. Will your language have functions as first-class citizens? Depends on what you mean. All right, so let's actually run the program. Breakpoint at label nothing. Okay, that makes sense. Step over in the instruction. Let's step the instruction. Push 64. All right, so this is the. Okay, so we're already inside of this entire thing. Can I inspect the memory? I forgot how to expand the memory. So if I put 10 in here, 10, 20. I think first is an address, and then we have something like this. Yeah. So, and it all depends actually on the size of the stack. Okay, so the size of the stack is 64, right? So here is the size of the stack, but I also want to be able to see, so I'm gonna actually provide 70 plus 8, 72, I think. So here is the stack frame, right? So this is the, I guess the position of the stack frame at the beginning of the frame, and this is the stack itself. Alright, so everything looks more or less okay, and we are ready to look at that. Okay, so then I read U, right, so then we can take a look at the stack. Okay, so the minus, where is the stack? I don't see the stack. Run, step over, continue program, print the stack, okay. All right, so the next one is going to be that. Push 8, minus 8. Duplicate 0. Okay, so far we're only like reading everything and preparing the stuff. Okay, so let me take a look at this stack. So here is the stack, which is kind of weird. There's a lot of shit on this stack. Oh, there's probably also return address and stuff like that. So yeah, that makes sense. And 072. And after that, yeah, finally, we actually, yeah, it did precisely what I expected. Perfect. It did precisely what I expected. So it basically referred again to the scope. This is actually perfect. All right, so then we do swap 1, and then we're essentially writing it back, and this is where we do that. And if I take a look, yeah, so this is perfect. So this is the address of the previous frame, and the current frame is actually 38, but 38 in hex is 56, right? It is 56, and if we take the whole memory in here, if we take the whole memory, so time 2, 56, just a second. I can't see shit. 56, boom. This one is weird, but It should point somewhere here, but it didn't. Oh yeah, I know. I'm sorry. I'm sorry. I need to somehow jump 56 words forward, but I don't know how to do that. So it's going to be meta f. Where is the meta f? Forward word. Okay, so all right. It points perfectly at the stack. Yes, it points perfectly. My gut. All right, so everything seems to be working, as I expect at least. So that means I didn't do any significant fucky-wacky and oopsie-doopsie. All right, so the next one is going to be returned, and then you hold the machine. Program is not being run. Perfect, perfect, perfect. Okay, thank you for reminding me about BDB. It's not particularly convenient, but at least you can inspect things with it already. So which is nice. All right, so here's we push in a new frame. Maybe this should be a separate like function, right? So push a new frame. Maybe we can even extract that. So bang, push new frame. Right, it's gonna be bang. It's at the UX level of good old DBX. Okay. Well, I mean, it's actually relatively intuitive. So I forgot how to use it completely, and I still recovered my knowledge. So good job. Actually, good job. So, all right, what do we have in here? And I can do something like this. Oh, by the way, the author of this debugger program is here at Some Plus. So he developed this debugger for the language. So it's actually pretty cool. Thank you so much. All right. So and in here we're actually asserting assert. This thing in here is going to be null. There we go. So push new frame. But now we need to be able to pop the frame, right? We need to be able to pop the frame. So let's introduce the function that pops the frame. I suppose static void bang pop frame bang. To be fair, we have to call it slightly differently. So it has to be called, I think it has to be called compile push new frame, right? Because it's a process of compilation, right? It's not like we're physically actually doing that on the level of the compiler. We're generating the code that pushes the new frame. Yeah, this is a better name, because we're not doing anything. We're just compiling the code that will do things at runtime. So that's quite important. That's quite important. Compile push new frame, and this one is compile that. Assert false to do compile pop new frame. It's going to be something like this. And interestingly enough, how are we going to be approaching that? Do we need the previous scope? I don't think we even need the previous scope, but we can do that anyway. Compile pop frame bang bosom. Alright. So the first step we need to do, we need to read the frame. We already know how to read the frame. So we might as well, by the way, extract these two lines of code into a separate compile function. Right. So because we need to do that quite often, we need to read the frame quite often. And I think I already repeat that code somewhere a couple of times. Yeah. So not only that, but actually this combination of two lines. Yeah, as you can see, I'm starting to repeat this combination of two lines quite often, already 3 times. And there is no explanation on what these two lines even do. But if we actually wrapped it into something more human readable, like read frame, read current frame address or something, it would be way easier actually. Hello Wiggler, hello. So compile read frame address, and it's going to accept bang bang bang, bosom, and we're literally just pushing this thing in here. Right, compile, read frame address, bang bosom. And let's find other places, other instances of this thing. Right, so that means I'm gonna compile, read frame address, bang bosom. And I want to have a lot of these like functions with semantically descriptive names. As we figure out more and more different patterns in here, I think we're gonna have more of them. What we do here, by the way, we're actually writing to the stack frame. So I'm thinking that maybe we're gonna extract this entire thing into separate stuff as well. So, but this one does the swap, right? I think it should do the swap, but I'm not quite sure. Okay, so let's not actually jump ahead of ourselves. Right, so let's just do this stuff. Okay, so we're popping the frame. We're reading the current frame. Works calls, enjoy your day, everyone. Bye-bye. See you around. All right, read frame address. Right, so read frame address. Okay, so we know this position where this entire thing starts. But do we really need to step back? I don't think so. Do we really need to step back? We might. It actually depends on how precisely all of that works. Oh man, this one is hard. Okay. Step back to read the pointer. So I suppose read previous frame address. Okay, so this one requires an understanding how all of that works on a level of specific bytes. So I have to be super careful in here because I might actually introduce some sort of a bug. So the reason why I didn't want to do that is because I just need a lot of like cells like that. So let's quickly draw them. So I'll definitely need them to understand. So, and I would like to number them as well. How are we gonna number them? It's gonna be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's go for maybe 12. Maybe 12 is gonna be alright. 10, 11, 12. So let's say that the size of the pointer is 4 bytes, right, for the simplicity. Right. And let's say that the size of the stack is going to be 8, right? So this is basically the stack. So that means it's going to end in here, right? So, and the actual stack pointer is going to be stored somewhere here. And what this thing should store? This thing should store the beginning of the stack, and the beginning of the stack is going to be it's gonna be 8, right? We're gonna prepare. So you have 13 bits in your segment. It doesn't matter. So let me see. Var stack. Prepare var stack. So I just push the stack size, and then I use the stack size as the address. So that means address, in fact, in reality, points at 8. Right, so it points at 8. So the next thing we do, I take 8 and I probably subtract at the offset. So I subtract 0 because offset is going to be 0 at this point, and push the current frame. I need to subtract the size of the pointer, which is going to be 8. And that means I'm going to be pointing at here, right? And then I'm just writing the previous address in here, right? So the new address now points at here. Okay, so that's cool. That means, okay, that's actually pretty cool. That means I can just read the frame address, then get the address, and then read it again and write it back there. Okay, that's actually pretty straightforward, I think. I think it's pretty straightforward. Cool. So let me see. So you read the current frame address. So read current frame address. After that, maybe I need to read it do the read one more time. So I actually do double dereferencing. There we go. Point at that. So, and now what I want to do, I want to write it back, right? I want to write it back. Write the prev frame back to the current frame. There we go. So that's what we're doing in here. We're writing it back. We are writing it back to back. So I want to maintain this stack super quick just to see what's going on. So first thing we do, we are pushing the frame, then we're reading it into the frame address. That's essentially what we're doing. Then we read that address one more time. So now we have the previous address. And interestingly enough, now I need to push the frame, and I suppose I need to swap it, right? So I'll need to swap it, because first thing should come the address where you're writing, and then the thing that you're writing. Okay, so let's go back. So that means I need to read the current frame, then swap the previous thing, and then write it back. And I think, yeah, I actually repeated the 3 lines that I expected to repeat, right? So I repeated these 2 lines, which means that I want to extract these 3 lines, not 2 lines. These 3 lines to a separate function. So write frame address, right? Static void compile write frame address. Bang, bang, basm, basm, boom, boom, boom. So what else do we have in here? It's gonna be something like this. And there we go. Compile write frame address. It's gonna be something like this. So it's already a little bit more readable. Deep Singularity, hi, haven't seen you in a while. How are you doing? Hi. Alright, that's pretty cool. So I like how pop in the frame is just like you read frame address, right? You read the current frame address, then you read from that address, and then you write it back. Alright, so so this thing is valid in here, and yeah, okay. I'm super happy with what I see in here, and let's take a look. So the assertion has happened. Oof. So I suppose Yeah, it shouldn't be equal to null, right? So it shouldn't be equal. Yeah, yeah, yeah. It's not that big of a oof. Not that big of an oof. Not that big of an oof. Not that big of an oof. So let me see. So how many instructions did we get in here? How many instructions did we get? I think like I want to have some sort of like a trace of execution where basically just a second. Right, I don't know what the hell was that, but let's continue. Let me see. I even forgot what I wanted to do. I think maybe I wanted to just try to execute everything, because I remember I checked that everything is working. Sonic's gonna release Jai 2 before... Nah, not really. I'm not trying to reinvent Jai. I'm trying to learn how to make programming languages. Jai is made by a person who knows a thing or two about making programming languages. The music is too loud, I think. I don't know anything about programming languages, and that's why I'm making my own programming language, just to learn that. It's more of an educational project rather than like a production one. So Jai is aimed at production. My language is really not, so... I have no idea what I'm doing, so... it is what it is. I just saw your GitHub, and your contribution activity is amazing. It's really easy. Just basically create a script that is automatically adds lines and removes lines from a dummy repo, and you're gonna have as amazing contribution history as I do. It's actually super easy, because GitHub doesn't care about the contributions, right? What kind of contributions you made, what's the quality of the contribution. It just counts how many commits you made, it just counts how many comments you made, how many issues you created. You can abuse that. You can easily abuse that, just make a script that does that for you, so it's goddamn easy. I thought, who writes? Do I look like a goddamn nerd? Do I really look like a goddamn nerd who writes code every single day? Hell no, of course not. Of course I didn't write any of this shit. Alright, so let's continue. What I was doing? I implemented the pop, right? We implemented the pop. And we just need to test how this entire... Oh yeah, I remember. I wanted to actually trace the execution, and essentially when I'm tracing the execution, I want to print the current instruction and the state of the memory. So line by line, instruction, state of the memory, instruction, state of the memory, instruction, state of the memory, and so on and so forth. Right, and that way I will see through each individual instruction like how the thing modified the memory and whatnot. I think it's gonna be goddamn cool. And that needs to be like some sort of like special mode of execution of bang, if you know what I'm talking about. If you know what I'm talking about. All right. So before we gonna implement that, I think I'm gonna commit whatever we have in here. All right. 4, 5, 8. Implement. I'm gonna sneeze, by the way. Debated. Implement a compile read frame address. Come on, you can do that. You can do that. I believe in you. All right. So implement these two functions, and let's push them right into the repo. So how are we going to be implementing this kind of mode? I think it's going to be part of the run, but with the run, we'll have to introduce like... Maybe we're going to introduce some sort of like a trace. Yeah. something like trace. But it requires compilation and whatnot. So let's introduce something like Boolean trace, which is going to be false by default, right? It is false by default. And here we're going to be parsing the command line arguments, right? So while you have that, no input file is provided. I see what's going on here. See what's going on. So input file path, we're going to be actually putting input file path in here, and then I'm going to just swap this thing around. If input file path is null, we're going to say no input file path is provided. All right. So if strcmp flag is something like I don't know, trace, we can use something like t. It's equal to 0. We're gonna set trace to true. Otherwise, we're gonna set the input file path to the current flag. I think that's how we do that in build subcommand, right? So that's precisely what we're doing here. Yeah, that's precisely what we're doing here. So here's the run subcommand. We can implement another flag in here, saying something like else if strcmp, I cannot type anymore, minus h, and it's going to be 0. Run, there was build usage, but I will also have a run usage, and it's going to be std out, and we're going to just exit with 0. And the question is, where is the run usage? Here it is. Okay, so and we also have options, right? Build usage. Yep. And so what kind of options do we have? Stream options. There's going to be a new line, fprintf stream. Build usage, so we have a space in there. 1, 2, 3, 4. Minus t is essentially enable trace mode, right? So enable trace mode. Minus h. I can steal this thing from here. There we go. Cool. So that's going to be the usage for the run command. So, and when we enable the trace mode, right? When we enable the trace mode, we're going to be executing this thing, constantly printing the current instruction and the state of memory. And the state of the memory. So I'm gonna go to here, and it's gonna be bm.c, bm execute program, where it is. So I suppose I'm gonna just grab this thing like this. We're not going to have any limit, I suppose. I don't think it's necessary. Then I'm executing a single instruction. Alright. So if it's not equal OK, we might actually put this thing in here. And then I'm going to be doing like that. And I think I can remove this entire stuff. Okay, so while we're not halted, we're executing an instruction, and if we encounter an error while executing an instruction, we're going to be just printing that error. We might as well actually inline this thing in here, right? If this thing is not okay, just, well, I mean, you need this variable, I see. I didn't notice that. All right. So, but if you are in the trace mode, right? If trace, we want to print the current instruction, right? We want to print the current instruction. What's going to be the current instruction? So it's going to be something like this. And the current instruction is literally just like that, right? So you take the current instruction and we're gonna print its name, right? It's gonna print f. We might as well actually print everything to the std error because we want to separate the output of the actual program execution and the emulator, right? So you may be able to redirect everything accordingly. So it's gonna be fprintf std error, and we need an instruction name. Where can I get an instruction name? So if I remember correctly, instruction itself, inst semicolon, has a type, right? And by the type, instruction type, you can get the definition of the instruction. Perfect. So let me see. So this is the instruction, right? That's pretty cool. And then you take the instruction type, and you get the definition. Right, here's your definition. And inside of the instruction definition, you have all sorts of stuff about this specific instruction. And for instance, the name of the instruction. So it's going to be def name. And here's an interesting thing. You can also have an information whether the instruction has an operand. And if, according to the definition, this stuff has an operand, you can also print that operand. It's going to be fprintf std error. It's going to be something like this. I think I'm going to put a space in here, and then we're going to do pri u64, all right, and only then I think I'm not going to put a new line in there. I don't think it's needed. So that means I take the instruction and just put an operand in here. So here's an operand, and after that I'm going to just be printing std error new line. There we go. Do you speak out loud when coding? Yes. When I'm actually coding and speaking out loud, I'm basically having a conversation with myself. So it's like pair programming, but with a single person, you know. Schizophrenia intensifies. So this is what we do during the tracing. But on top of that, I want to then execute the instruction, and I want to take a look at the state of the memory after executing the instruction. You know what I mean? Here's a question. I'm not sure when do I want to print that. I think it makes sense to actually print it like after we executed the instruction. If trace. And I just want to print a particular, size of the memory. How are we going to be doing all of that? So we're going to have bang trace memory start, which is going to be 0, and then memory size, which is going to be 72, I suppose. 72. It's all fun and games until you have an argument with yourself while debugging something. I do that all the time, by the way. All right. So we're gonna do. So this is going to be the start, and I think these two things has to be customizable somehow, but I'm not quite sure. Not quite sure. Okay, so we're going to start with 0 less than memory size, and there we go. All right. So then we need to construct a memory address. Hello Anthrax, const address, and what I'm doing here, I'm taking the start and adding I. There we go. So, and what I want to do in here, probably I also need to pad this stuff a little bit. It's going to be fprintf std error 1 2 3 4. I think 4 should be enough, and then maybe even 3. Fprintf std error space 02x 02x, and we need to do the following thing. bm memory address plus I. There we go. So, and after that we're gonna do fprintf GA got me. All right, so okay. So then we put a new line. Good fucking dead. So this is how we're going to be doing the tracing, I suppose. All right, let's try to compile this entire thing. This is not how we compile it. Semicolon, by the way. So we do debusm, that should be fine. But when I'm tracing the thing, oh man, when I'm tracing the thing, I actually have to specify the size of the stack. Okay. Well, I mean, I can do that, I suppose. I think it shouldn't be that difficult. bm, okay. bm dot. Anything else? LU expected but long. Oh yeah, as U64, I suppose. Yesu, kawaii desu. Wait, yeah, okay. Execute instruction, this one has to be pointer, of course. stdr. Come on, man. Alright. Hands up. That's cool. So when I'm running the thing, right, so I have a trace, and I want to also be able to specify the stack size. Yeah, so let's do it like that. So it's going to be stack size, local variable stack size in bytes. And s. Oh, okay. Well, at least I can copy paste this stuff. You know, the truly reusable code, as I say, is the one that you can copy paste. So you see how easy it is to reuse this stuff. Right, so it's gonna be query replace build usage run usage. There we go. Okay, good. So and then we have a stack size, and that means we have to have something like size t, stack size equal to bang default stack size. Stack size, and here you go. And now there is a way to customize this stack size for bang rang, so I don't even need to report that as an issue, which is perfect. So it's gonna be stack size. 10k line, one needs to spend hours configuring CMake. Yeah, that's true. Truly reusable, so easy to reuse, my god. It's so easy. You just add it to your CMake and it just works. Okay. Bang run needs a way to customize bang and these two things. So right now they are hard-coded, but we need to customize them somehow. It is something that is absolutely needed. Alright, so everything seems to be compiling. So I may try to run my application. So right now I'm building the application. Now I'm going to be running it. So, okay, so it worked, right? And I specified a stack of 64. If I put something like this, it should tell me that the stack is incorrect. And it didn't. Thank you very much. So it means it didn't work. What the fuck? I'm disappointed. I'm extremely disappointed. Stack size. So if excuse me, you're supposed to work. So let's put it this way. Gonna print f stack size zu stack size. Is it even compilable? I don't know. I'm actually doubting. Okay, so it literally didn't work. It didn't care. So what if I put this thing in here? Please don't tell me that I forgot to recompile, because I'm recompiling right now and it literally does nothing. Am I running something incorrectly? I'm compiling the new bang every time. What am I missing? So here's the flag. This is true. H. What if I try to do something like minus H? Is it gonna work? Okay, it does work. Huh. It's really strange. So H worked, stack didn't work at all. That's really strange. Okay, so I suppose I need to debug that, because I don't see the problem in here. Alright. I probably don't see it because I'm already tired, actually. So let's do GDB. And I wish I could just run it like that, but I can't run it. So that means I have to do something like this. Maybe I'm gonna use the tmux. Right, so it's gonna be GDB and run this entire thing. Before I run it, I want to break run subcommand. Right, and let's just run it. TUI enable. Alright, so here's the trace, and let's take a look at the flag. So here's the flag, minus H, and it will then exit. Okay. So what about actually run, but without H69? Yeah, start. Oh my god, holy shit. So display flag. Let's try to display this one more time. Can I print the flag then? Okay. How does it work? Am I going crazy? I'm pretty sure, like, I missed something very, very dumb. The input file is always the first argument. It shouldn't be the case. It shouldn't be the case. There's a shift before the loop. Oh, holy shit, okay. Thank you so much. So I already, like, it's difficult for me to stream, interact with the chat, and also think about very complicated problem at the same time for 3 hours. So I really apologize that at the end, like towards 3 hours, I'm starting to make very stupid mistakes. I'm sorry. All right, so okay, stack size is gonna be something like that. All right. Okay. Let me see. So I want you to just run this entire thing. H is not a correct one, so if I put ABC, It also should be not correct one, which is nice. But if I put something like 64, it is going to be a correct one, and it executed something. At least it didn't crash, which is important. At least it didn't crash. So let's now try to trace this entire thing. Okay, so we've got the trace. So did I put that on a new line? Yeah, I think I put that into the new line. So that means while we're tracing this entire stuff, so this is a new line. We don't need this space in here. I don't think it's necessary. I think in like 64-bit is too much. What about 32? Is it gonna crash? It might actually crash, but no, not really. So here is that. We might try to split this by cells of 8, right? By cells of 8. We can try to do that, yeah. Trace memory, bang, trace. So essentially I want to actually go through several cells, right? So size I, cell less than how many? 4, right? So we're gonna have 4 cells. Right, and then within a single cell, we're gonna have a byte from 0 to byte less bang trace cell size. So, and this is gonna be bang trace cell count, right? So this can be plus byte, like this. And essentially here, we're going to be printing it like this. Right. So it's going to be f stdr, and so I probably need to calculate the address first. So the address first is going to be the beginning of the address plus cell multiplied by the cell size. Cell size plus byte. There we go. So we have a memory start plus the current cell plus the byte offset within the cell. Right, so that's basically what we're doing in here. And we can just do it like that. There we go. So, and at the end of the cell, what I'm thinking is that maybe we're gonna actually put a new line. I think that would make it a little bit better. We can also put a little bit of that. And essentially you're gonna have an instruction and then several chunks of the cells. So memory start, we do care about that. Cell count in this case is going to be something around like 4. Cell size is obviously going to be 8. Bank needs a way to customize trace mode parameters. Right, trace mode parameters. All right, so if I try to run this entire thing, I don't want to clutter. Yeah, perfect. This is what I wanted. My God. Okay, go. I suppose 4 of these cells is not really enough, right? If the size of the stack is 32 bytes, can we even see? So this is 16, this is... yeah, we cannot see shit in this mist, so that means we need to at least have 5 of the cells. Alright, there we go. Here is the entirety of the stack, and here is the frame stack. Okay, that's perfect. I really, really like that. So we push 32, read, blah, blah, blah. And I'm waiting until write 64. Okay, as you can see, we did write 64, and then push 32, and then did another write, and now the current frame is actually something that is closer to that. It would be also kind of cool to have like addresses in here alongside. I think we can do that. I think it should be relatively easy to do. So in here we're gonna have something like 0 to maybe like 4x and like this. So it's gonna be sort of like a hex editor, if you know what I'm talking about, right? And this is gonna be something like this. 0x, and that means we need to have this as a separate variable, right? So a const memory address start, right? So this is where we start this entire shite, and here start plus byte. Okay, so I can recompile this entire thing. Holy shit, I did a fucky wacky. Maybe possibly even oopsie doopsie, because I forgot a new line. Alrighty, so what do we have in here? Still does not compile, because I have to provide the start. Alright. Anything else? Expected x, xl, lx. Well, I'm really glad that compiler at least tells me what I need to have in here, which is super nice. Std error. So we're almost there. We're almost gonna see the trait. Perfect. All right. This is actually cool. Like Emacs, like colored it accidentally properly. All right. So after the first write, we saved this thing, and then on the next write. Yeah, so you see the current frame is 18, and here is the address of 18. It starts in here. Okay, perfect. So then we're gonna do another write. Yeah, after another write we are restoring the previous frame, and then we're returning. Okay, this actually works perfectly. This actually works perfectly. I really like that. This mode is actually pretty cool. So yeah, that's precisely what I want. It's a little bit better with than the debugger, because I can basically rewind back and stuff like that. So yeah, that's very cool. Okay. Well, I'm programming in programming language called C. Sindura Tubeworm, hello. How are you doing? Welcome, welcome, welcome. Okay, again. I guess I'm more or less satisfied with how we push and pop the frames, and I would like to actually test something more extreme. For instance, I want to add something like if true, right, which effectively adds another frame in here, right? My everything hurts, but okay. Oh my god, I hope you're fine. I hope you're fine as well, Mr. Stream. I'm alright. Trying not to get burned out yet again, but getting really close to it. Okay. So, what do we have? So here we're introducing yet another scope, and maybe inside of the scope I want to have some arithmetic operations like a 69 plus 420, right? And I want to see if this entire thing will, you know, crash or not. So if I'm gonna, yeah, let's just try to build it first, right? Let's try to build it. And it didn't really build because I'm in a wrong folder. Alright. Okay, it seems to be building, and after that I may try to do debusm bin debusm foo bm, and let's take a look at the output. Fuck. Okay. See, yet another case. I forgot about the stack. So, speaking of why you shouldn't use Emacs. Alright, so this is going to be debusm, and so stack is going to be 64, right? So should be a little bit smaller now. No such folder. Oh yeah. Stack 64 when I'm building everything. Alright. So I just wanted to see what is going on. Yeah, here we're pushing 69 and 420, and then we're dropping it, and then we're popping out the stacks and whatnot. I loaded FreeBSD SRC into my Git the other day. It was a mistake. I can imagine. So I'm actually using my Git for a very long time, and also I've been using it on big production projects. And yeah, so on big projects I usually just go back to command line. Yeah. Cheers, by the way. But my Git works really well on small projects. So, and if I try to run this entire thing, it seems to be running, but it doesn't have any side effects. I would like to introduce some side effects just to see if it works correctly. So something like hello world. Right, so let's see if it's gonna print hello world. And it printed hello world. Would you look at that? That's actually pretty cool. Let's try to trace this entire thing and see how the memory is updated. Oh, 64 is now bigger, so maybe I actually have to do 32. 32. Can you see shit in this mist? I wonder why. It's all 0, no matter what. So let's try to... I don't understand, because... Oh, I'm an idiot. I was looking at white zeros, but I forgot that you have to look at the green ones, because Emacs colored them like this. Okay, so we have 20, then you have 80, alright. And at some point you actually have to go deeper. Yeah, so then it becomes... Yeah, okay. Look. This one, the current frame is 10, and the address of 10 is this one. The previous frame is 18, and 18, and then 20. So they sort of form like a linked list, if you know what I'm talking about. So the current frame is 10, which is that one. And here we have 80, which is the previous one, which contains 20, which is the previous one. And this is how you can sort of restore back to, like along the stack. But each frame doesn't contain anything, so that's why they're like really close to each other. Right. And at some point when we hit the halt, the current frame is going to stay 20, right? So, yeah. I can actually have several, like ifs, several layers of ifs. True. Like this. And let's see how it's going to go. So right now, none of that is optimized away, but it's optimizing all of that stuff is kind of outside of the scope of what we're doing right now. We're gonna have like a separate stream where we're gonna write optimizer, which removes like useless crap. We'll see. Oh, okay, so that's pretty cool. So at some point, yeah, it should have actually... It's almost overflew. Oh my god, look at that. Right, so the current frame is 0, 0 contains 08, 08 contains 10, 10 contains 18, 18 contains 20, 20 contains the current one. Right, so I think if I add yet another condition in here, the application will stack overflow. It's not circular because we're not following in the circular way. Yeah, there we go. So with enough if truths, you can actually overflow your stack. This right now in our language overflows the stack. Well, I didn't say my language is good. My language isn't finished, right? I'm in the middle of making it good, okay? So yeah, so right now the way the stack works, you can overflow the stack with enough like truths and stuff like that. But I mean, it's kind of easy. You just set the stack to something big, like 4 kilobytes. And I think I don't want to do that with the trace mode on. I don't think I want to do that with the trace on mode because it's gonna print all of that shit onto Oh, well, it won't. Okay, as you can see, it doesn't overflow, so... All right, so there we go. All right, so I'm actually super happy with what we have in here. So what we introduced in here, I think we introduced like a special tracing mode. That's what we did. And 458, introduce special tracing mode for bang run. So that's what we did in here. I'm gonna push that right into the repo. So interestingly enough, we still haven't solved 558, believe it or not. 558 was about compiling the stack variable, right? And we still can't compile stack variables. So because we didn't have any frame system in place. I suppose, yeah, we can try to implement the compilation of the stack variables, but it will require updating top frame. Okay, let's give it a try. So I'm gonna go to the example in here. So we have example foo, right? Foo bang. And what I'm gonna try to do in here, I'm gonna try to do x I64. Well, you cannot assign it anyway. All right, so let's try to compile this entire example and run it and see what's gonna happen. All right, so compiling the stack variable is not implemented. How would you compile a stack variable? So that's a very, very interesting question. So we need to go back to the drawing board. Drawing board doesn't want to cooperate. Hello, the Thenor, welcome to the stream. Hello, hello, hello. So here is your stack. So let me grab this kind of stuff. I'm all over the place. I cannot find my place in this society. All right, so here's the current frame, right? So here's the frame, right? Frame. And then somewhere here, right? So there's like stack. I might as well actually draw that a little bit better, like so, right? So this is where we have the previous frame, and in here I'm gonna just put something like this. Right. So, and the current frame in fact points somewhere here, right? It points actually, yeah, it will point somewhere here. So this is where all of that starts. And this is where we have free stuff. Okay, so, and the free memory is located somewhere here. Oh boy. All right. So compiling a new variable. To compile a new variable, we need to find this place, like the place where we can place that variable. Right. So that means first thing we need to do, we need to read current frame, right? Read frame address. Right. So we read frame address and we found this specific place. Right, so we found this specific place. Then we need to subtract the scope of set. So this specific offset is kept tracked by the scope. Right, so by doing the second step, on the second step we identified this place. So this is the first step, identifying this place. Then the second step is identifying this place. Then we need to know the size of the variable we are allocating, right? We need to know the size of the variable we are allocating, and we need to offset by the size of the variable. offset by size of variable. Right, and this is what we will find on a step 3. So this is a step 3. On a step 4, we need to update scope of set. Right, so we need to update scope of set because now scope of set is going to be this one. It's going to accommodate this variable. See what I'm talking about? Yep. So what's interesting is that on the scope end, when we end the scope, yeah, when we end the scope, we can just like pop out the frame, and everything inside of like this frame is going to be forgotten completely. All right, so update the scope offset. Offset, there we go. So read frame, sub the scope offset, offset by size of a variable, update the scope offset. All right, so we need to implement that to be able to compile local variables. We only will be able to compile them. We won't be able to read them, and we won't be able to write into them. But I think once we are able to push this scope frame, pop the scope frame, and allocate variables on the scope, reading and writing from that variables is actually quite trivial, because reading and writing is just figuring out its address, which is frame and offset relative to that frame, and just reading and writing there. So yeah, so maybe if we manage to implement that, implementing the rest of the things is going to be trivial, and we're finally going to have local variables, because it's kind of difficult to develop without local variables. They're not required if you want to have a Turing-complete language, but if you want to have a convenient language, you kind of need local variables. So we wrote like 100 lines program that simulates rule 110, and we did that without any local variables. You see, we allocated all of the variables in the global, and it was fine, it works, but it's not particularly convenient, right? So we did that just to prove that the language is Turing complete. All right, hello Shigman, how are you doing? Cheers, by the way. All right, I suppose we need to just implement this thing. Read the frame. Luckily, by the way, we already have a function to read the frame, which is super cool. So yet another like pattern that is getting reused like several times. So compile read frame address. Yeah. 1, 2, 3. So we already do the like read frame address 3 times, and we're gonna have a 4th one when we're trying to allocate a variable, right? When we're trying to allocate a variable. To be fair, wait a second. Read the frame. No, to compile the variable, I think we don't even need to read the frame address, because the compilation of the variable is just like calculating all of the necessary positions and stuff like that. It is not needed, I think. I think compiling the variable is much easier than I think. I think I overcomplicated it because I'm already tired. All right, so I think it's literally a single step. Yeah, all of that is a runtime shit. Yeah, I just need to update the scope of set. Right. Okay, so let's give it a try. Is that stack-based virtual machine? Yeah, it's stack-based, but the situation there is actually a little bit more difficult. So we have a stack for arguments, but we also have a separate stack for local variables inside of the memory of the virtual machine. So the virtual machine has a stack for operands and a static memory, but there is no place for local variables, so we store local variables in the memory. So there's like 2 kinds of stack, operand stack and local variable stack, which is emulated. So, and you can find the source code of this entire stuff, of course, here. Yeah. So first we developed a simple virtual machine, and now we're developing a language on top of that, a simple virtual machine. Okay. So let me go here, and here is existing variable. So the variable does not exist. The variable does not exist. So first thing I want to do, I want to compile the variable, right? So compile compiled var, compiled var var. We can call it like a local variable. It's a local var. So what's going to be the definition of the local variable? The definition is going to be var definition. Here is var definition. And the type, do we know the type of this thing? Bank. Wait, why do we have a type in here? I think the type, yeah, we do know the type. Local variable type is equal to the type. And the storage. The storage is the most interesting part, by the way. Storage is going to be equal to bang var storage. What kind of things we have there? Is it stacks? Yeah, it's a stack storage. So it's stored on the stack. And then we have a memory address, local var address. And in case of a stack storage, this address is essentially offset from the stack frame. Right, so we have the so that means we need to take the bang scope, right? So we need to take the current scope and we need to take its offset, but I forgot what is, like how the variable is called. I need to find bang scope. And this is a frame top offset. Frame top offset plus the size of the variable, and the size of the variable is the size of the type. And to get the size of the type, we need to find the definition of that type. Right, I think we have a special function that gets the definition of that type. Get so something about type definition. Yeah, so here is the type definition, and you can get the type definition with this function, right? So essentially, get type definition, type, bang, type def, type definition. And inside of that thing, we have the size of the type. Is it a C-like programming language? I don't think so. Does C have generics? I don't know. Does C have arrays? C does have arrays. So I have a lot of plans actually for this language, and it's gonna be as simple as C, but with modern things like compile time execution. What do you need with in 2021? In 2021, any decent native programming language has to have generics, compile time execution, some sort of like a macro system, and so on and so forth. So it's going to be C, but modernized C with the modern things that you would expect from such language. C11 has a generic macro. It's not a generics. Underscore generic macro is not generics in a sense of parameter of a structure. Generic, by generic we usually mean a type that is parameterized by another type. In case of C11, generic is basically function overloading with the manual mangling. That's what it is. So in C++, function overloading works the following way. The compiler takes the functions that have similar names, dispatches according to their types, and then mangles their names. So in the final output, they actually have different names, right? So basically, generic is the same thing, but you mangle the names of the functions manually. It has nothing to do with classical understandings of generics whatsoever. And this is not even that useful, because what I found is that generally C developers don't really care about function overloading. They are okay with mangling function names manually and actually directly calling by those function names, so they don't really care about this kind of stuff. It's kind of really weird feature, and it's really out of place. I don't know why they introduced it. Okay. So let me see. So this is going to be something like that. Type def, and what I need to do in here, I actually need to get the type definition. Okay. So it's offset plus the size of the variable, right? So, and we know for a fact that it is not void because you can't allocate the void, so it should be fine. So we might as well also assert something like that this thing is greater than 0, just in case, just in case in the future something like this fails. All right, and after that, I guess I need to push the new variable, right? Compile static var definition, right? And at the end, I just push the new variable into the scope. So this has to be called like a local variable. We replace local var new var. There we go. Okay, so that looks fine to me, but I also forgot to maybe update the top offset. So we might as well actually put this thing like that, and then the actual top offset is going to be the address in here. The address in here, so let me see if it compiled or not. Yeah, let's actually try to run it and see how it goes. C4 bits empty initialize. Okay, sure. 0. Alright, so we don't use bosom in here, which is kind of sus, not gonna lie. Oh yeah, I know why. Huh. Because compiling stack variable doesn't require generating any code. Yeah, it doesn't require generating any code because we only need to keep track of the offsets, and the only code that needs to be generated is for reading and writing variables. Okay. All right. So that kind of makes sense, I suppose. So that means in here I'm gonna remove this thing, and then we're gonna have something like this. So stack var, and I'm gonna explicitly remove the boson from here. So this is going to be something like this. All right. So it seems to be compiling, and okay, so I think it even compiled. Yeah. So, and it even run. So if I take a look at the full bang, okay, that's perfect. That's pretty cool. So I can even try to do something like write hello, right? And it's going to work. But what's not going to work is reading or writing into these things. If I try to initialize this variable, it's gonna fail with assertion, saying that assigning to a stack variable is not implemented. Perfect. So if I move this thing outside of the local variable, right? Plots. If this is something bad, feel free to ban them, permanently ban. Is it something bad? Is it something MongoDB? Because I don't know. If it's something MongoDB, insta-ban, perma-ban them. Don't even think about it. It is perma-ban. Don't even think about it. Don't even think about it. I can actually perma-ban them myself. X54, we do not approve of whatever this person said. Okay, let me see. I actually like this proc syntax instead of a fan. Yeah, I think function, the notion of a function is a mathematical one, right? So it's a basically mapping from one set to another. There's nothing functional about programming functions. They are sequence of instructions. They are procedures. I don't know like why programmers stole the word functions from mathematicians and completely changed the meaning of that thing. So yeah, it was kind of weird. But yeah, thank you for telling me that it's something bad, because I don't speak German, so I don't understand what it is. All right, so, and yeah, it's the same as with the C++ vector, right? There's nothing, by vector we mean a notion from a linear algebra. There's nothing common between std vector and a vector from linear algebra. Like, why the fuck this thing was called vector? This is a dynamic array. What the hell? It's just like, it's kind of weird. Like, programmers keep stealing random words from mathematicians and just completely changing their meaning. It's like... All right. So, what I'm thinking. I'm thinking, yeah. So effectively, I fixed this problem, right? Effectively, I fixed this problem. Now we are capable of compiling local variables. We still cannot read and write into these variables, right? And we have separate issues for that, right? So you see, it compiles, but I cannot read and write into that. And this is something that could be addressed in the next time. All right, so let me see what we did in here. Seems good to me. Seems good to me. All right. We can try to actually test all of that on our big examples, like rule 110, just to see if it still works. Well, that was unfortunate. I should have actually went here and let me see. Okay, so it seems to be working. What about game of life? By the way, Heroes and Plots, if the person that we banned today will start whispering you shit, feel free to report them to Twitch immediately. So, okay, so everything should be okay. Because I deal with this kind of people every day, so I know their reaction to this kind of stuff. All right. So it seems good. All right. 558. Okay. Implement the compilation of the local variables. Okay. Let's push that right into the repo. Okay, let's create a pull request. So we managed to implement a pretty cool functionality for our language. We introduced the notion of the frames, and we generate the code that pushes the new frame onto the stack and pops the frame out of the stack. And we also keep track of the offsets within the frame of the local variables. So effectively what we did, we implemented the compilation of local variables. We cannot read from them, we cannot write into them, but we can compile them. So that's actually quite important. So maybe I can just implement the compilation of the local variables. All right. And let's do something like this. 58, and this one is going to be closed. And I wonder if I introduced any to-dos to snitch up. So it's going to be go bin snitch list unreported. Let's take a look at what unreported things we have. Yeah, bang run needs a way to customize the trace mode parameters. This is true. Get the actual size of the pointer from the definition of the pointer type. So yeah, I'm also gonna report that. So for those who doesn't know, this is a snitch, and snitch is basically a tool that I use for collecting to-dos from my source code and reporting them as issues. It is really convenient. I'm gonna actually put that thing in the description as well for people on YouTube, for lovely people on YouTube. Because this recording of the stream is also gonna go on YouTube tomorrow. So subscribe to the channel if you don't want to miss that. Right, so we're posting it on this specific channel. Snitch. There we go. So, and let me see. So, yeah, I wanted to report this thing. So we're going to be doing report, and I also want to prepend body saying introduced in 468. 468. All right. Needs a way to customize trace parameters. All right, the actual size, and there we go. And it will use GitHub API to report all of these issues. Here they are. Here they are reported. Would you look at that? There we go. It's pretty convenient. Yeah. Okay, that's the easy way to get ignored from now on. So let me see. I think the Windows was actually failing. So let's wait until it's done. All right, I guess I think I'm gonna go. Today was a pretty productive stream, but unfortunately, boys and girls, I'm a little bit tired. I'm streaming for 3 hours, and I think today was a good stream. Today was a good stream. Thanks everyone who's watching me right now. I really appreciate it. Have a good one, and I see you all tomorrow. Tomorrow, I don't know what we're gonna do tomorrow. Maybe something. It just depends on my mood. And yeah, so thank you for all of the subscriptions, for all of the bits and stuff like that. Yeah, love you all. Mwah.